We are asked to find the Thévenin equivalent circuit for this network that we see below. In this case, looking at these resistors, we see that they are neither in series nor in parallel, and so in order to find the Thévenin equivalent circuit, we will need to find the open circuit voltage and the short circuit current. We should end up with an equivalent circuit that looks like this. A Thévenin equivalent circuit is a voltage source in series with a resistor, where the Thévenin voltage is the open circuit voltage and the Thévenin resistance is the ratio of the open circuit voltage to the short circuit current. So our first step will be to find the open circuit voltage. Our open circuit voltage is when there's an open circuit, there's no connection between terminals A and B. And when we're looking for a voltage, the best way to find that with a fairly complex circuit is to use nodal analysis, since that will yield for us the voltages at each node. We'll pick a ground. The bottom of the circuit is a good place to pick the ground. Also, by putting the ground at the bottom, we know that we have 72 volts here due to our source. We do have an unknown voltage at this node, and we have an unknown voltage at this node as well. We will then label our currents. And we will write a KCL equation for each node. Next, we rewrite these equations in the form that will make it easier for us to put into a matrix. Plugging this into a calculator, we can find V1 and V2. We found that V2 is equal to 64.8 volts, and V2 is measured relative to the ground, which is at the bottom. So we see that V2 measured from this node to the ground is the same as the open circuit voltage. Thus, the open circuit voltage is also 64.8 volts. Now, we want to put this value to the side, since this is a part of what we're going to need for our Thévenin equivalent circuit, but we also need to find the short circuit current. That means that we're going to have to reanalyze this circuit with a short circuit in place between the terminals A and B. Now, we're trying to find this short circuit current. If we're looking for a current in, again, a fairly complex system, the easiest way to do that is going to be to use mesh analysis. And so we will define our mesh currents for the different meshes that we have in this circuit. And notice here, the only mesh in our short circuit is I3. So once we find I3, that will be our short circuit current. So we'll start by writing mesh equations for our three different meshes we have in the circuit. Next, we rewrite these equations and organize them so that we can plug them into the calculator. We can use a calculator to solve for the mesh currents I1, I2, and I3 as well. We noticed at the beginning that the short circuit current is the same as I3, and we found I3 to be 10.8 amps. Thus, the short circuit current must also be 10.8. Now we can take this value and put it with our short circuit voltage. That's all that we're going to need to solve for our Thévenin circuit. We saw that the open circuit voltage was 64.8 volts. Thus, the Thévenin voltage is the same as that open circuit voltage. We have a 64.8 volt source, and our Thévenin resistance is the ratio, the quotient of the open circuit voltage divided by the short circuit current. In this case, this is going to be 64.8 divided by 10.8, which will give us 6 ohms as our Thévenin resistance. Thus, by finding the open circuit voltage and the closed circuit current, we've been able to find a Thévenin equivalent circuit to this much larger and more complex network.